Hi, this is just a quick video to help you to solve problem 3 on your in-class problem set 8B. So please read over this problem before you start. And once you've done that, you can look at the reaction that's shown here and the data. And the first question is just asking you, part A here is asking you, what's the difference between the reactions for which the data are written here. So here we have two sets of data. This is reaction 1 and reaction 2. And for reaction 1, there's an R group that is H, so we're talking about this R group up here. And for reaction 2, the R group is CH3. So basically what we've done here is we're going from a secondary amine ligand, or two secondary amine ligands, to tertiary amine ligands. And that means that from reaction 1 and 2, we're increasing the steric bulk. So in other words, the real difference here is that reaction 1 has less steric bulk than reaction 2, because reaction 1 has secondary amines, whereas reaction 2 has tertiary amines. Part B here is asking you to remember why the mechanism of a square planar substitution is typically associative. So you can basically just use what you know to please rationalize this on the basis of sterics and electronics of the square planar DA complexes. So that's two things. And as far as sterics go, remember that these square planar metal complexes have two open faces. So if I draw my metal complex like this, where two ligands are coming out of the plane and two are going back, I have this whole open space here and here, these open faces where ligands can enter and without much steric resistance. So this is really a nice, easy path of very low resistance. And as far as the electronics go, these square planar metal complexes, if I define this as Z, for example,
they have these d orbitals that are perpendicular to the plane of the molecule
that are very easy for ligands to interact with. So if I draw my dz squared, for example, you can see that the ligand would easily be able to interact with that orbital. I can also draw maybe a dxz or dyz orbital here. Both of them would be perpendicular to the plane of the molecule, and it would be really easy for ligands to come in and interact with those orbitals. And so for these reasons, it's easy to see why most of the time square planar complexes react with ligands through associative mechanisms. So part C is where I would expect that you might need some help interpreting what is being asked here. We know that the square planar complexes typically react through associative mechanisms. This isn't referring to the mechanism necessarily, but referring to the pathways by which these things can react. So it turns out that solvent participation can often facilitate or compete with the incoming ligand, and so you can actually form an intermediate with the metal complex bound to the solvent molecule. So these are the two pathways that I'm looking for in this problem. So here I've drawn my palladium complex with a cartoon of my tridentate chelate with the chloride bound. The one direct pathway is where iodine directly replaces the chloride and you get your product. And I'm going to define the rate constant for that reaction as K1. And so my rate equation for this type of a reaction, or this pathway, rate would be equal to the rate constant times the concentration of the palladium chloride complex times the concentration of the incoming ligand. In a second pathway, I'm representing here solvent as S. The solvent, like water for example, can replace the chloride first and give you a palladium solvent intermediate. And you can read from this problem that this is typically the rate limiting step. And then I assign here a rate constant of K2. The next step is where iodine replaces, or the incoming ligand replaces the solvent. And since this is fast, I'm not going to write a rate constant there because it's not the rate limiting step of this pathway. And so the pathway rate expression would be this step here is rate limiting. And so rate is equal to K2 times the concentration of the palladium chloride complex. And the solvent is not part of this rate equation because the solvent concentration is so much greater than the concentration of the palladium chloride that it doesn't change much in the rate during the reaction. And so it's kind of part of this rate constant. Now, writing the overall rate expression for this reaction just means that you combine the rate constants of the you combine the rate expressions of the two competing reactions. And so here, my overall rate then is going to be equal to the rate expression for the first pathway plus the rate expression for the second pathway. So they're both happening at the same time. They both contribute to the rate of disappearance of the starting material. And I can simplify this. If I remove the palladium chloride complex if I basically separate the palladium chloride complex from the rate constants, I get an expression that looks like this. And then I can further simplify this and say that the rate constants here times the concentration of that the rate constants here and the initial iodine concentration can be combined or basically represented as K obs, or the observed rate constant. And that would be multiplied by the concentration of the palladium chloride complex, and that is my rate expression. Rate is equal to the observed rate constant times palladium chloride. In this case, K obs is equal to K1 times the concentration of iodine plus K2, where now, I can think of this as a linear equation. Y is equal to mx plus b, where this would be the intercept and this would be the slope of a linear equation. So from a plot of the concentration of iodine versus the observed rate constant, I can pull out the slope, which would be the K1, and the intercept, which would be K2, the y-intercept, which would be K2. So then using this information here, you can solve part D. So this says that using the plotted data and the linear equations for each data set, give the microscopic rate constants for the competing reactions. So here, if I look at the reaction number 1, here's the slope of my line, and here is the intercept. And so this should say K1 and K2. And I'm sorry if yours doesn't. But K1, there is the slope. So K1 here is about 3,500. And K2 is the intercept, so that is about 25. And for reaction 2, I have a slope of about 1 and an intercept of about 0.25. And so now I know what my microscopic rate constants were for reaction 1 and reaction 2. And for part E, now I just want to look at this data here and compare. Notice that the rate constants for reaction 1 are much higher than the rate constants for reaction 2. What does this reveal about the mechanism? Well, remember, this was less steric bulk, and this was more. And so as we increase the sterics, we're actually decreasing the reaction rate. And this is very typical for an associative mechanism. And so what this reveals about the mechanism is that it is, in fact, associative.